Most of the most dangerous security bugs in history, like Heartbleed, Straight Freight, Eternal Blue, were not crypto bugs, not network bugs, they were memory bugs. So before we talk about sanitizers, hardware tagging, or Rust, we need to understand one thing clearly: why memory is unsafe in the first place. Once you get this, everything else will feel obvious. When we say memory, we don't mean storage like SSD or SDD. We mean RAM, the working memory of a running program. RAM is just a big array of bytes. The CPU doesn't know variables, objects, or string. It only knows addresses. Everything your program does, variables, array, objects, is just reading and writing memory addresses. Most programs use memory in three main regions: stack, heap, and globals. The stack is automatic, function calls, push data, return pop data. The heap is manual. You have to manage the memory manually. In case of heap, you ask for memory and you must give it back. This manual control is powerful, and this is where things start going wrong. Languages like C and C++ follow a trust-based model. The compiler trusts the programmer. If you say this pointer is valid, the compiler believes you. If you say this memory is still alive, the CPU doesn't question it. There are no built-in runtime checks. And that's not a bug. That was a design choice for performance. Most memory bugs are not intentional. They happen because programmers' mental model and memory's reality drift apart. Let's take a simple example. You allocate some particular memory. You use it, then you free it. But later, you still have the pointer. The pointer looks valid, the address exists, but the memory is no longer yours. This is called use after free. The CPU does not stop you. The OS does not stop you. The program keeps running. For example, I have this demo code. If you can see, this code has a serious bug. We are allocating a particular memory to this pointer. We are assigning a value here, and then we free it. After freeing this pointer is no longer valid because we have freed, right? But look here, the pointer still has an address, and we are using it to print the value in it. And if you run this program, see, it compiles cleanly, no warnings. And if I run it, then you will see it prints the value also. If you can see value 4 here. This is undefined behavior, but nothing stops it. This value can be anything. This can be crash also. So using this freed pointer, we don't know what will happen. This is undefined behavior. So this is a serious bug of use after free. So the next question comes into our mind: why these bugs survive testing? We do tests, right? Every program we push for production. Here's a scary part. Most memory bugs don't crash immediately. They depend on timing, allocation pattern, what runs before or after. So the same bug may work 1000 times and crash only once, or become security vulnerability. That's why memory bugs survive testing and show up in the production only. So now we understand the real problem. The system trusts the programmer, and programmers make mistakes, right? Everyone can make mistakes. So the question becomes, how do we catch these mistakes at runtime? That's where our journey into memory safety really begins. In the next video, we'll see more about these memory bugs. And then after, we'll start learning about sanitizers, which we generally use to detect these kind of bugs. And remember, we'll keep it simple.